This is all a bit of a painful process, but there's actually an easier way to work out some of these integrals, and that is by using Gauss's law. Now let's look at an analogy. I have some fireflies in a jar here. Each one gives out a certain amount of light. Suppose I can't count how many fireflies are in the jar. Is there another way I could get out that information? I could look at the amount of light coming out and calculate the number of fireflies, or if I know the number of flies, I could calculate the amount of light that would be coming out. Now Gauss's law works on a similar principle. If we know the charge inside a volume of space, we can work out the amount of electric field going in or out. It also means that we can work out the charge inside a space by looking at the amount of electric field, but we won't be doing that here. The challenge is there are two signs, and so the field direction counts. Now there's a new symbol here. Phi means the total amount of electric field coming out of a surface. It's called the electric flux. It's sometimes given the subscript E because you'll see later on that there's also magnetic flux that we give the symbol phi sub B. But for now, we'll just call it phi. Gauss's law says that the total electric flux out of a surface times the permittivity for air, E naught, will be equal to the charge inside the surface. We often see it written as an integral, which uses A as the area of the surface, and says that if you were to add up the field coming out of each little bit of surface and times it by E0, it will be equal to the charge inside. Electric flux is easy if the electric field is constant. It's just the electric field strength, E, times the area A that it's going through, times the cos of the angle between them. So it's a maximum when the field is perpendicular to the surface, but 0 when the field is parallel to the surface. If the field isn't constant, we have to use integration and add up each little bit of field multiplied by each little bit of area that it's going through. What can make it much easier is that we only need to consider the component of the field coming straight out through the surface at right angles to it. If we choose our surfaces carefully, many of those terms can turn out to be 0. So, to sum up, we pick a 3D surface that encloses our charge. We divide it up into little bits of surface area. We look at the electric field perpendicular to each bit of surface, multiply them to get the flux through each little bit of the surface area, and then we add all the bits of flux together. It all looks complicated, but we're going to choose some examples where it's fairly easy. The first example is working out the field around a point charge. We already know what that is. We saw it in the last lesson, and so we should end up with a familiar-looking equation. For this point charge, we are going to choose a Gaussian surface around it that is a sphere. Now, it could have been a cube or a cylinder or a pear shape, but the sphere has got two advantages. Firstly, every little bit of area dA is the same distance away from Q, and secondly, the electric field is perpendicular to the surface at all points, so we can forget the cos theta term. Let's look at the working.